In the first part of this section, you learned how to manipulate functions so that you could analyze them analytically. You also had to rely on the knowledge you gained in section 1-2, finding limits by making tables and by graphing your functions. Combining these three approaches is going to lead us into a new theorem called the squeeze theorem. This theorem is going to help us analyze other limits and also look at special trigonometric limits. Using all of these techniques together, we're going to be able to now find limits of some very complex functions. In your book, the squeeze theorem is defined as a function f of x which lies between two other functions, h of x and g of x, in a particular interval. Now, if we know that h of x and g of x have the same limit at a particular value c within the interval, then we can expect that not only does the limit of f of x exist, but that it will be equal to the limit of the other two functions, which is L. Let's look at this in a visual sort of way. Let's say that we have a city, and our city is located right there. Now, coming through our city from the north, we have a highway, g of x, and it travels through our city and then takes off again, going to the north. But there's also another highway coming from the south, h of x, and as it reaches the city, it travels through, joins g of x just for a moment, and then takes off again towards the south. Now, if we were to build another highway, and the restriction on this highway was that it had to cover the area in between the other two highways. No other restrictions. It could do anything it wanted, but it has to remain between the other two highways. As it approaches the city, the other two highways squeeze it so that it goes right through the city. And then once it passes through the city, it again has its freedom to do whatever it wants. But the two highways squeezed the middle highway and forced it to go through that particular city. This theorem, in addition to being called the squeeze theorem, is also called the sandwich theorem or the pinching theorem because it forces another function to go through a particular point. Now let's look at this from a more analytical perspective. If I look at the graph of our three functions, and I know that f of x lies between g of x and h of x for all values of x, then I can graph g of x. I don't know what it's doing before or after x equals 7, but I know that right at x equals 7, that g of x is approaching 10. And likewise for h is below f of x for all values of x. But as x approaches 7, h also approaches 10. Therefore, if our function f stays between the other two functions for all values of x within the interval, the first two functions will force f to travel through the value of 10 as well. So without even knowing what function I have, what values of y it has anywhere else on the graph, I know that as x approaches 7, the limit of my function is 10. Now let's look at a special trigonometric limit. I want to find the limit as theta goes to 0 of sine of theta over theta. If I look at this in an analytical method, I would look at sine of 0 over 0. Now, you might already say, well, because it's undefined, we can't determine what's happening. But even worse, sine of 0 is 0. And when I have 0 over 0, what we call that is indeterminate. And that means I can't make any conclusion whatsoever. I can't say that the function has a limit that's d and e. I can't give any value or any conclusion at all. So I fall back to my initial lesson on finding limits, and that was by using a table. So looking to the left, I start at negative pi over 4 and work my way towards 0. And then I start at pi over 4 from the right and work my way towards 0. And it would appear that my limits are going to be 1, even though 0 is an undefined area. But I also want to look at this graphically. And I want to use my squeeze theorem that I just learned in order to help me. So the first thing that I think about is that sine of theta, it ranges between negative 1 and 1. Even though it's being divided by theta, which will alter it a little bit, I know that I could use a function g of x and say g of x equals that horizontal line y equals 1. And so graphing that as a function, and then the next function that I'm going to use is going to be cosine, because cosine and sine have such a close relationship. I know that sine maxes at 1, crosses at pi over 2, and mins at pi. And it does the same thing symmetrically across the y-axis. So looking at the graph of cosine between negative pi and pi, and knowing that my graph, sine of theta over theta, is between the line y equals 1 and the graph of cosine for all values of x between negative pi and pi, graphing my sine of theta over theta with the use of the table above and also the table in my calculator, so you guys can graph it in your calculator and take a look at the values I was using. And I look at it and I go, oh, look at this. It's lying between these two graphs. Here's my g of x. That equals 1. Here's my h of x. That equals cosine x. And here is my f of x. That equals sine of x over x. And so as I look at this and I say, okay, my graph is in between these two graphs, and the squeeze theorem says that it's pulling them, squishing it in between these two, that even though there's a hole right here in my graph, from the left, I'm approaching 1, and from the right, I'm approaching 1. Therefore, the limit as theta approaches 0 of sine of theta over theta is 1. This is a special trigonometric limit. It's the first of 2 you're going to learn. You need to put it in your flipbook and memorize it, just like you memorized your trigonometric identities, because we're going to use it a lot. Now for the second trigonometric limit that we need to learn. We have the limit as theta approaches 0 of 1 minus cosine theta over theta. And we look at it, and again, if we plug this in, we get 1 minus cosine of 0, which we know is 1. So we know that that's 0, over plugging in 0 for theta, over 0. This is a problem, again, because it's indeterminate. We are not allowed to determine anything from taking the analytical perspective. So I'll look at my function, and that 1 minus cosine theta on top really encourages me because I look at that and I see something very close to a trigonometric identity that we learned last year. We learned that 1 minus cosine squared theta was sine squared theta. And since this is half of that factor, I can multiply by the conjugate. And notice I'm going to multiply both the numerator and the denominator by the same thing. Because this is an expression, not an equation, we can only multiply by a creative value of the number 1. So I get my 1 minus cosine squared on top over theta times 1 plus cosine theta on the bottom. And I use my identity. And notice that I can break this up and say that I'm really finding the limit as theta goes to 0 of two different fractions. I can break this up into a product because the limit of the product times the limit of the product is simply a product of the limits. Those are your properties of limits that you learned earlier in this section. Okay, so we know that the limit as theta goes to 0 of sine of theta over theta is equal to 1. That's what we just learned about a special trigonometric limit. And then we look at the second half and we say the limit of sine of theta over 1 plus cosine theta. Well, sine of 0, now let's use an analytical method because we fixed it so that we could. And I get 1 times 0 over 1 plus 1, which is 1 times 0 is just 0. So the second very important trigonometric limit that you need to memorize, put it in your flip book, memorize it just like your trigonometric identities. The limit as theta goes to 0 of 1 minus cosine theta over theta is equal to 0. So now we're going to do some problems. We've got about 4 examples. They're going to get steadily more difficult, but I want you to see what we do for each one and how we manipulate them so that you're able to use what you know in order to solve something that becomes steadily more difficult. So I look at this particular limit and I say that if I take the limit as theta goes to 0, again, I'm going to get an indeterminate form. But notice how close this looks to that special trig limit as theta goes to 0 of sine of theta over theta. If I look at this as my angle, the 7 theta is my angle. Well, I just need to alter this part to make sure I can get them to match because it's got to be sine of theta over theta. So I'm allowed to multiply by a creative value of number 1. So that's exactly what I'm going to do. I need a 7, so I'm going to multiply by 7 over 7. And I get sine of 7 theta over 7 theta. So now this part looks just like my special trigonometric limit that I can use. I'm going to do a substitution. I'm going to replace my 7 thetas with x, and I'm going to take the limit as x goes to 0. I have that 7 out front, and then I have sine of 7 theta, which I'm replacing with x, over 7 theta, which I'm replacing with x. This portion right here, we know, is equal to 1. The limit of a constant is that constant, and the limit of two products is the product of the two limits. So we get the limit of 7 theta over theta as theta goes to 0 is equal to 7. Now, for our second example, we want to find the limit as theta goes to 0 of cosine theta tan theta all over theta. Now, notice our only special trig limit that we have is the limit as theta goes to 0 of sine theta over theta. If we can't make it look just like this, and it has to be just like it has to say sine of an angle over a matching angle, then we cannot say that it's equal to 1. So I don't have a rule for cosine theta over theta. I don't have a rule for tangent theta over theta. So I've got to start playing with this and seeing what can I make it look like. So I'm looking at the tangent portion and I'm saying, you know, that's pre-cal, that's a trig identity. So I'm going to rewrite it. So breaking it up into two fractions, I have cosine theta over 1, and I have tan theta, which is really sine theta over cosine theta over theta as a fraction that's theta over 1. I'm going to take that and I'm going to reciprocate my denominator. So I have cosine theta over 1 times sine theta over cosine theta times 1 over theta. Because we don't divide by fractions, we multiply by their reciprocal. Simplifying algebra, I cancel my cosines, and I end up with the limit as theta approaches 0 of sine theta over theta, which is my identity. So I know that that's 1. My final answer. For our third example, we're going to find the limit as theta goes to 0 of 1 minus cosine theta over sine theta. Now, we know if we plug 0 in, we're going to get 1 minus 1 on the top, which is 0, over sine of 0, which is 0, and that's indeterminate. So I want to use some identities this time to make this fraction rewrite itself so that I can actually plug in my theta equals 0. So there's a couple different ways because of the fact that we're using identities. So I'm going to divide the screen in half and do this twice. So the first time I do it, I'm looking at the 1 minus cosine theta and thinking that that is so close to 1 minus cosine squared. So we're going to start by multiplying top and bottom by the conjugate to make that identity show up. Remember, we can only multiply by that cute little number 1 because it's an expression, not an equation. So we get 1 minus cosine squared on the top. On the bottom, I get sine theta times the conjugate. Do not multiply the bottom. You're always looking to see if something will cancel. So on the top, I have sine squared. I'm going to write it twice just so that we can see it and evaluate what we have. Okay, so the signs cancel, and that means we can take the 0 at this point and plug it in, and in the top we get sine of 0, which is 0, and on the bottom we get 1 plus cosine of 0, which is 1 plus 1, and 0 over 2, just 0. So the limit is equal to 0. Now, Looking at it again, this time I'm going to multiply top and bottom by sine. Again, another reference to the number 1, but this time I'm going in a different direction, trying to get a different relationship to show up. So on the bottom I have sine squared, and if I factor that, well, not really factor it, but use an identity, sine squared is really 1 minus cosine squared. So I can replace it, and that can be factored. And so, as I take the limit, as theta goes to 0, of sine of theta over 1 plus cosine theta, it's the same as saying 0 over 1 plus 1, which is 0. Same answer, slightly different method. For our final example, we're going to take the limit as t approaches 0 of 1 minus cosine 2t all over sine of 3t quantity squared. Now this may look complicated, but think about what you've been learning about for the last couple lessons. You've been learning about properties and special trig limits, and then combining that with your trig identities that you've had since last year. The whole idea of calculus is to take the small pieces, break things up so that you can answer small questions and put those answers back together to get the answer to the big question. So you'll notice I broke all of my factors of my fraction up into 3 small fractions, because if I know the limits of each of the products, then I can take the limit of the products and multiply the limits together at the end. So if I look at the small 1 over sine of 3t fractions that I made, I know that the limit as theta goes to 0 of sine of theta over theta is equal to 1. Now 1 over 1 is a fraction. If I follow that idea and I say I want to take the limit of the reciprocal of my special trig limit, then the answer should be the reciprocal of the answer, which is just 1. So I'm going to take my fractions out front. I'm going to multiply by a special number 1 that will allow me to do a substitution to use my rule of my limits. For now, I'm going to leave the 1 minus cosine 2t alone, and we'll talk about him in just a minute. So, grouping what I have, because these are what I'm going to do substitution on in just a second. I'm going to keep my fractions because these have that special trigonometric limit. I'm going to combine my 1 over 3t and my 1 over 3t and get 1 over 9t squared. Now let's talk about the 1 minus cosine 2t. The cosine portion of it, the cosine 2t, that's a double angle identity, which you guys would remember has 3 separate identities that we can replace it with. My favorite ones are 2 cosine squared t minus 1, or cosine 2t could equal 1 minus 2 sine squared. t. Okay, I'll look at what I have in just a second to decide which one I want. So that's going to go right here. 1 minus whichever expression I decide to use. Okay, so I'm going to let x equal 3t. And I get the limit of x over sine of x as x approaches 0 times x over sine x. And I'm looking here and I have 9t squared. Now that 9t squared is a problem because if that equals 0, then I have an undefined answer. So I want to make something happen that's going to go away. So again, I'm looking back at my original limit of sine of theta over theta and thinking, wow, I am so close to this version of it. And so I think what the one I want to use is the 1 minus 2 sine squared theta. Although I could have used the first one too. It would have come out the same in the end. It would have just been some extra steps. So as I simplify this, I get 1 minus 1, which is going to be 0. And then a negative carried into that negative makes that positive. So I have a positive 2 sine squared t over 9t squared. Now this part, I want to give it a different limit because its variables are different. So I want the limit as t approaches 0. Now breaking that up, that's the same as the limit as t approaches 0 of 2 times sine of t over t, sine of t over t, and I'm going to bring that 9 and just put it under the 2. So, taking my limits as I go, I have the limit as x approaches 0 of x over sine x. These are both 1, 1 times 1. I've rewritten this one in this form. So now evaluating the limit of a constant is the constant. So now I'm multiplying times 2 over 9. And then sine of t is 1, sine of t over t, and sine of t over t, again, that's 1. So my answer is 2 over 9. So now it's time for you to try it on your own. So I have 2 different questions that are very similar to examples that you've seen. Don't forget some of the techniques that I've shown you. Make sure that you have all of my examples written down in your notes. And if you need to, go back and rewatch the video so that you get those techniques very fresh in your mind. Submit these answers to me before 6:30 tomorrow morning. Thank you. Now for your homework for this section, we're going to be doing some more examples tomorrow in class. Make sure that you ask questions. You're welcome to come in during reading period, during lunch, or after school. I'll see you tomorrow.